Hello everyone and welcome back. Welcome to part 2 of this course on the anaerobic power reserve concept in cycling. Here you again see the outline of the course that we also discussed already before. In the previous chapter we discussed some basic definitions and principles of the anaerobic power reserve and specifically showed some of the research on that within cycling. As mentioned already also in the previous chapter, then in this chapter specifically, we start to focus more on the testing approaches to determine the anaerobic power reserve and also some other tests to determine some other variables. We already highlighted also in the previous chapter when we were talking about the research how the anaerobic power reserve has been assessed in these research settings, so either via laboratory-based testing or via field tests. And today we'll go through some of those different approaches in some more detail, and I will also give some recommendations from my side at least on how you could assess certain variables within a practical setting. So before we dive into the different testing protocols, I thought it was good to just firstly give some general considerations around testing. So as you can see highlighted on the screen here, I think we can make a distinction between more physiological based testing and I guess in a more laboratory based setting, or at least within settings where we have the ability to take some physiological measurements. So you can see one example on the left from a training camp from last year. We are actually taking some physiological measures, so you can see we're taking some gas exchange measurements and we're also taking some lactate measurements. So this is obviously not per se then a laboratory setting, but it is a setting at least indoor where we have a little bit more control about the environmental considerations and where we then have the ability where the rider is on an indoor trainer where we can then take some physiological measures that is often that's not possible when they're riding out in the field. So it's not per se a laboratory-based setting, but at least a setting where we have a little bit more control and where we can take some physiological measurements. So besides these physiological assessments that therefore occurred so in a laboratory setting or in more controlled environments, we also have quite a wide variety of testing possibilities in the field. That's largely due to the sort of advancement within technology and the advancements with the use of mobile power meters. We can now actually gather a lot more data in the field. So I would like to call these assessments are more functional assessments, which are assessing the functional capacity in an ecologically valid way, so where there normally also will be training and racing. I will also go through some examples of that specifically later on. Besides that, of course, we can do some specific performance trials and performance data that we collect from training and races in the field with the use of those mobile power meters. Now, regardless of the testing approach, in my view, testing services two main goals. One is for rider profiling, so to get as much information as possible about the rider's characteristics and the useful information we can get from that to prescribe training and determine training focus points. And then secondly, for training prescription. So a lot of the tests that we do, for example, to determine a specific threshold that has direct implications for training prescription. We will use those thresholds or markers to set training boundaries and training intensities. So let's keep these goals a little bit in mind when we go through the next slides. So if you then look at testing approaches from a practical perspective, firstly, as I mentioned there, the aim should then always be to get as much information as possible from the athlete without putting a large burden on the athlete's training program, so to speak. So obviously we would all like to collect a lot of data. We would like to have very frequent tests, but very frequent tests also take away proper training time. And also from a periodization perspective, it might not always be warranted to do maximal trials in the field in that specific training phase. So we need to find a little bit of a balance here, because ideally for some tests the rider should also be well rested. So if that then takes away some of the training time that we would do, that makes it sometimes a little bit more difficult to implement, because some of these tests can actually be quite invasive to the athletes already quite busy schedule for training and racing. So we need to find a bit of a balance there, and I'll show you some examples of that. And often this is just case by case and logistics dependent. Furthermore, we need to consider the signal versus the noise. So we want to have a test that's valid and reliable, and with a high sensitivity and relatively low variation. Because if the test is not sensitive enough to detect relatively small improvements, which we will typically see within professional athletes, then obviously the test will have limited impact. So that's what we also need to consider. And also, I would say maybe it's a little bit of an obvious statement, but I would still see it sometimes in practice, that we're just measuring something for the sake of measuring. So in my view, we need to only measure variables that can actually directly inform practice. So we need to make a little bit of a distinction between tests that give data and information that's just sort of nice to know, but don't directly inform training practice, and tests that can directly inform decision making. Because we have already limited time, especially with elite athletes, we need to be a little bit smart about that and try to do as least possible tests but get the most information. So in the end, you're balancing out logistical considerations with the optimal test. So there is, for sure limitations to, for example, field testing, limited control over environmental conditions, for example, but field testing significantly increases the possibility to more frequently assess the athletes. So that's then a balance that you then have to make. So if you look a little bit further into different variables that we can assess that will have an impact on training decisions and training prescription, I added this figure from the review from Martin and Paul that I also highlighted in the previous chapter. And this figure actually shows a variety of markers that occur at different points on the intensity spectrum. As you can see, they're highlighted within this figure. So maximal sprinting speed determines the upper limit of this intensity continuum. And if we move further down, we can identify, for example, the maximal aerobic speed, as you can see over here. And obviously, as we discussed in the previous chapter, the difference between these two, or the range between these two, is then called the anaerobic reserve. If you then move a little bit further down from this, you can then identify the critical speed, or perhaps you can assess a maximal lactate steady state. So the critical speed and power concept is also what we discussed already a little bit in the previous chapter. But what this basically shows is that with a number of markers, we can then start to determine sort of an intensity spectrum for each individual. And then subsequently, you can fit your intensities, let's say for high intensity interval training prescriptions, where you can see some of the examples here mentioned on the right, based on a percentage of those different markers. So you relate your intervals to the threshold or marker within the closest proximity. So that's mainly just an example to show you assess different variables, all at a different sort of point within the intensity continuum, and that can subsequently inform training practice. But for missing out on some of these variables, we're not actually getting the full picture. So remember again what we showed in the previous chapter, where we looked at two cyclists that had the same maximal aerobic power or very similar, but their anaerobic power reserve was quite substantially different. So if you want to truly individualize training, we would like to have multiple data points across the whole continuum. And then actually taking that same concept that I showed in the previous slide, but then applying that to cycling, was actually very nicely mentioned in a book that recently came out from Phil Skiba, called Scientific Training for Endurance Athletes. And here he basically described sort of a similar continuum of intensity, but then conceptualizing that as a house. So I'll just talk you through that. He started that house sort of with the foundation, or the endurance capacity, which is then where the upper limit is set by the lactate threshold. Then he had some additional markers. So he had sort of the roof line of the house determined by the maximum aerobic power, and the ceiling within that house is then determined by the critical power. Then we have the roof, where the upper limit is determined by sprint peak power output. again, as you can also start to now see similarities with the previous slide, but then sort of this is then conceptualized as a house. So again, we move from lower intensities, so more endurance training intensities, if you like, and I move up in the continuum to critical power, up to maximum aerobic power, and then to the highest intensities with sprint peak power output. Then obviously again, the roof then sort of conceptualizes the anaerobic power reserve. So I thought this is a very nice example on how you could conceptualize this intensity continuum, and with some of those testing protocols that we'll go through, we'll in the end aim to sort of build this house for each individual. So with this course, we're obviously specifically looking at the roof of the house, so the range between maximal aerobic power and sprint peak power output, the anaerobic reserve. So while some of these other methodologies to determine thresholds will also be mentioned, it's not per se the largest focus of this course. And we'll show it to just put it in full perspective, but the main focus will be on testing practices to determine the anaerobic power reserve. So let's then start at the top. How do we assess sprint peak power output? Well, as you can already see here in these images, we can make a differentiation between more laboratory-based assessments, like on an SRM ergometer that you see on the left, where there's a lot more possibilities to control certain factors. So you can, for example, keep the cadence consistent or constant when you do certain trials, or with the field-based assessment. So we mentioned before the mobile power meters, and obviously we can do maximal sprint trials and collect the data using that way. You can basically identify some pros and cons to both approaches. So if you look at the research into the anaerobic power reserve, we can then basically also identify two main approaches that have been used within the research. So the study by Peter Wayne et al., which I extensively discussed in a previous chapter, they actually used a laboratory-based assessment where the upper limit for the anaerobic power reserve was determined using the highest power output the participants were able to maintain for 3 seconds at a constant cadence of 100 RPM seated. So they used an ergometer for that within a laboratory-based setting. Now the benefit of this approach is of course the standardized conditions. So you have limited variability between measurements, and you can actually keep a lot of variables actually consistent. So if you would have to choose the ideal method from a research study perspective, this would obviously be the way to go. The only difficulty with this is that if you like to translate that to the field, it's obviously this is quite difficult to do without the specialized equipment, and it's if not impossible to do within the field. And with a normal bike setup that most road cyclists will have, this would actually not be possible. So another thing that we actually have seen in practice is that riders are also not able to achieve the same numbers indoors and outdoors when doing a sprint. So if we then want to use the numbers that they achieve indoor, which is normally somewhat lower, to prescribe training outdoor, that might also be somewhat problematic. So that's factors that we have to consider. Now in the studies that we did, we then actually used a field-based approach because we were working with professional cyclists, and again taking into that consideration that we wanted to have as least of a burden as possible. We then performed multiple out-out standing sprints in the field and then determined the maximal 1 second peak power output they could achieve. The benefit of this, of course, is that it's very easy to do in the field. However, it can also add quite some variability. So it no control for environmental factors. We could control the gradients to some extent by giving them advice on where to do the sprints, but there is obviously some more variability with that if you do it in the field. And also we couldn't control the cadence. So that's a little bit the balance that we have to take. I would argue that if we want to apply these methodologies in practice, obviously the second approach would normally be more widely used and more widely applied because of the easy to use nature of it, and because of a higher ecological validity when actually performing it in the field, because of some of those differences that we can see between indoor and outdoor numbers when performing sprints. Now, since those studies we've actually started to look a little bit more into determining sprint peak power output, and best determine that. So this is a figure from a study that's actually under review at the moment, which should normally cross the line fairly soon. It's a study led by Kurt Berg and Taylor, which is a colleague of mine at Team DSM, who has quite some experience with sprint protocols coming from the track. So the main reason actually for looking a little bit more into this is that, and the research is pretty clear on that, is that riders can present with varying power cadence and varying torque cadence profiles. So what you would typically see is that there's a curvilinear power cadence relationship, as you can see here illustrated for two different riders, and we see this linear torque cadence relationship, again illustrated for two riders. But yeah, as I said, we can see varying profiles within if you would actually assess that. So that means that some riders achieve their sprint peak power output at a different cadence, optimal cadence if you like, compared to another rider. Secondly, the maximal cadence and maximal torque some riders can perform can also be quite different. And there's quite some factors that can contribute to that: fiber type, activation, relaxation, kinetics, coordination, all factors that could play a role to determine these between individual differences. But actually the interesting thing is when we actually look at two sprinters, we can also identify quite some differences in the power cadence and torque cadence profiles, even if they present with relatively similar peak power outputs. So even then they could, let's say they could sprint 1700 watts. It might still be that if we determine these profiles, that for one sprinter that occurs at a somewhat higher cadence than it does for the other sprinter. And then same, the torque cadence profiles can also look somewhat different. So taking that information into account, again together with my colleagues in this study that will hopefully be published soon, we have looked a little bit into a field-based way to determine these individuals' sprint peak power output and these different profiles to a greater extent. So what we would then suggest is that you would actually perform multiple sprints in the field with different gearing ratios, which you can actually all do within a single session. So you can see here perform multiple sprints between 6 to 8 seconds in the field, and you can see here some different gearing ratios that are suggested. You can see seated sprints, standing sprints, which is all based on some pilot testing that we actually have done. And based on the information that we collect from this, we can actually start to model those power cadence and torque cadence relationships. So we can identify what the optimal cadence is for peak power production for this athlete, which can then impact, for example, decision making on gearing selections within races. And secondly, we can then start to model their theoretical max cadence and maximal torque, which gives us information about the profile of the athlete and potential windows of improvement. So with this protocol, you would be able to increase the chance of determining a true sprint peak power output, as well as modeling these important parameters, which can subsequently individualize the training prescription. So for example, if we determine this torque cadence profile, and we can see that some athlete is somewhat lacking on this torque front compared to our reference numbers, with that athlete, if that's a goal to improve that further, you can then implement some more high torque sprints. And furthermore, also, if we think about off-bike training, strength training, for example, this information can also be of relevance when aiming to individualize some of the content within strength training and focus points within that. So this would be somewhat more advanced way of determining sprint peak power output if you compare to some of the previous studies, but definitely a lot of information that you could get from that will impact practice. So that was the sprint power output. Let's now move towards determining maximal aerobic power. If we again think about that, we want to determine this anaerobic power reserve range. Similar as with some of the other examples, we can then look again at either a lab-based, as you can see again with the example over there, with gas exchange measurements, for example, either in a setting like that in a training camp or in a true lab, or we can use different field-based estimates to get to that. Again, both will have their pros and cons. So if we think about a direct determination, so actually truly assessing it, yeah, the gold standard way of doing it is to do an incremental REM test to exhaustion in a laboratory setting with gas exchange measurements. That's obviously, yeah, also that's the gold standard measurement. The one important consideration with this that I would like to mention is that it's protocol dependent. So depending on the increment, starting power output, this can impact the eventual maximal aerobic power you can determine. Best practice would therefore, yeah, be to whatever protocol you go for, obviously based on the scientific recommendations, stick with that for future comparisons. Otherwise it might be difficult to compare different testing protocols with each other. So that's the gold standard measurement, but actually the same pros and cons apply to this that we also discussed before. If you think about a professional cycling team, a World Tour cycling team has 30 riders, getting 30 riders through a laboratory protocol like this, where we can only often test one athlete at a time, that's obviously quite time consuming and quite invasive. And also these labs are obviously not available everywhere. So typically they would have to be flown out somewhere, athletes live across the whole world almost. So that then makes it, again, quite difficult to start to implement that. That's why you also saw in the previous slide that we started to experiment with mobile gas exchange measurements, which we can actually take to a training camp to do some measurements with. But you can imagine that it is more invasive, and the frequency of testing is seriously reduced because of that. So that's a negative that we have to, or negative thing that we have to take into account. Well, if you want to indirectly estimate it, so not actually determining it, but estimating it, there's a few proposals within the research how that could be done. So one very simple one that's proposed by Burton et al. In the late 90s, but also by some other research, is to actually do a 5 to also some other research suggesting a 6-minute all-out, evenly paced effort, as that would then roughly translate to some of the maximal aerobic powers that they have observed to determine in a laboratory setting, for example. This is mainly based on research on the time to exhaustion at maximal aerobic power or maximal aerobic speed. And the study that we actually did was a field-based protocol incremental test where we ride 6 by 6 minutes on a climb at increasing power outputs, where the last effort is actually a 6-minute all-out effort. And then that last stage could then be used as an indirect estimate of the maximum aerobic power. Not per se too dissimilar from just doing a 6-minute all-out test, but obviously there's sort of a preceding fatiguing element perhaps from the sub-maximal steps. But the reason was that we used those previous steps to determine some lactate measurements to also more get a sub-maximal profile on that end as well. Another protocol that has been proposed, and this is also mentioned by Phil Skiba in his book, is to sort of use a modified University of Montreal test, so sort of an incremental field-based test. And Phil Skiba then suggested to have 2-minute progressions where you start out at sub-maximal power output and then progressively build up the power with those 2-minute increments. And then the last step that you can maintain for 2 minutes to complete for those 2-minute durations, that's then in the end, that will in the end then determine your maximum aerobic power, or an estimate of that at least. So a lot of different protocols. My general advice would just be choose one that's a validated protocol, so ideally something based on the research and something that you can repeatedly assess. So I think that the perfect test that you can only do once a year, it obviously has minimal practical impact. Let's say you do this test only at the start of the year, obviously that gives you some information at the start of the year and perhaps for the months following from that. But when things start to shift, when you get towards the competitive season or within the competitive season, ideally you would like to continue to test this at multiple times to have an idea how things are progressing. And again, often you end up, especially when I think about road cycling, with some of these field-based estimates. So in the previous slides, we have been discussing the utilization of doing field trials and having athletes or cyclists do maximal efforts in the field to get information from. And there's actually, as we were also discussing, a lot of information that we can collect with these heart rate belts and with mobile power meters. So there is a lot of things that we can actually do in the field. So what I wanted to show you here is actually, when we're talking about these maximal trials, I just wanted to show you then very quickly how that would look like if we would analyze a training file where one of those maximal efforts is performed. So as an example here, we see an overview in Training Peaks of a rider who completed a 4-hour ride, and within this 4-hour ride, he did a 6-minute effort, 6-minute max effort. So if you think about this 6-minute effort, how nicely that fits in with some of the protocols that we have discussed as then a potential estimate of somebody's maximum aerobic power or the lower bound of the anaerobic reserve. Now, for those that are familiar or at least are working within endurance sports, this is quite a familiar sight, and it shouldn't be particularly new. But yeah, what you could do with software like this, and this is not the only software out there, there's multiple ways how you can analyze the files. But you can see, for example, based on the GPS, where the rider has done his ride. So in this case, it was in Andorra. And then at the bottom here, you can see the data that was collected with the different devices, so with the heart rate belt and with the mobile power meter. And then you can start to see the inputs from those different, or the outputs from the different data channels that were collected during the ride. So you can see here in the background this gray sort of surface or piece here that determines sort of the riding profile. So the elevation gain, it describes the elevation gain. So in this section is then obviously uphill, this is a descent, and again an uphill portion. And then all the other colored lines sort of represent the different data channels that we have. So we have, for example, in pink here, the power output that the athlete was producing for this ride. We have in red the heart rate data trace. We have in green then also the speed that was achieved throughout the ride. So if you look at the descent, for example, we can see here that the speed is the highest. In yellow, we have then the cadence that the athlete was producing. So you can start to get a pretty detailed idea what the athlete did at what time point within the ride. Most of these data channels have a data collection frequency of 1 Hz, so you have a data point for every second for all of these different channels that you see over here. So this is obviously, you can start with your first analysis of, okay, what's the average power for the ride, what's the average heart rate, what time was spent in different intensity zones. There's a lot of ways that you can then start to analyze this data a little bit, but what we are particularly interested in is actually that 6-minute effort for this example. So you can already identify a little bit here, this part where the athlete is on a shortish climb, and where you can see that the power and heart rate was actually substantially elevated. So we can already identify the 6-minute effort quite quickly. So if we then zoom in a little bit, which we can do endlessly, we can then see how these different data traces vary. So you can see here in pink that the power is fairly low to start with. Then this section that is highlighted here, that's when you can see when the 6-minute effort starts. So you can see this increase in power output in pink, and that just then stays for a power output trace actually fairly evenly paced throughout the 6-minute effort. You can then see that there's a little bit of a lag in the heart rate response, of course, as expected, that then take some time to catch up with that increase in the external intensity. Now that we have that 6-minute effort, then we can start to look a little bit at what the numbers show. So it was 6 minutes in duration, of course, as we wanted. We have a gradient at 6.7%, so that the effort was done on the climb. And then we can start to look at what the data channels show us. So we can look at minimum, maximum, but also the mean, which we are in a lot of cases most interested about. So we can see here, for example, if you look at the average power, that was then 439 watts. Heart rate was on average 181 with a max of 190, and the cadence was on average 81 RPM. So that's then Yeah, just a pretty basic example of how it would then look like in practice if we start to do some of these max trials in the fields that we have discussed. So this is then an example of a 6-minute effort, but depending on the protocol and depending on the goal of the specific effort, that will then can vary in duration. But at least to show you in practice how also remotely you can actually analyze the data that comes in, and then this is then the first analysis of what this number then looks like, and then you can start to put put that more together when you have when some of the other tests are also performed. And one element I also just wanted to briefly mention. So in our last study, we also looked at different parameters to include within the modeling approaches. So we used the original approach that you can see over here and looked at mean deviation and mean deviation as a percentage. We also did that for different approaches, mainly again just to explore a little bit what happens if we change some of these input variables to a different variable. So for example, we also modified the exponent to some extent based on some least squares analysis that we did for some participants. And one of the things we showed there is that if you use a 3-minute power to set the lower end of the anaerobic power reserve, that it also worked fairly well, and perhaps even somewhat better. But theoretically, that doesn't really make sense for what I was just saying. So the 3-minute power is of course somewhat too short as a maximum aerobic power output measurement if you look at the previous studies looking at time to exhaustion at the maximum aerobic power or speed. So this might make it a little bit confusing, and I guess there's also some factors within this study and the trial durations which were actually only up till 3 minutes, the record power outputs that we included, that can actually contribute a little bit to these results. I still wanted to mention it, even though it might be a little bit confusing, but long story short, if you have a blank sheet and you would like to test maximum aerobic power estimated in the field, I would advise to use a slightly longer protocol. So let's say 5 to 6 minutes, which is more in line with the recommendations in the research that I just showed you. Now, another topic I would like to cover quickly is the analysis of record power outputs. So here you see a typical graph which includes maximum mean power outputs across a long duration spectrum for an athlete of one season. And one of the things that I've been asked before is if you have this information, which also includes their ability to perform within the short duration domain, which is the domain for the anaerobic power reserve, of course, do you then actually still need the anaerobic power reserve? But I think it's a good question, and there's also a lot of information that we can get from a graph like this. And the more information we have about an individual using data like this, the less needed the APR might be. But where I actually see it slightly different, as I mentioned in this slide. So basically with the APR you have two inputs, and you determine the whole duration spectrum subsequently, or you can do that using that formula that we discussed, but up until like 300 seconds. But as you saw in the previous slide, you can also get that information from the maximum mean power duration curve to have an understanding about what their maximal capabilities are for this variety of durations. That's true, but the difference is actually that the maximum mean power duration curve only becomes representative of close to maximum performance after you have collected a large amount of data for months or even a year. So if you analyze a full season, yes, then it gives you a very good picture. But what if you start with an athlete after the off-season, for example, and you want to determine their capabilities within this short duration domain and powers within that? Yeah, like it's too invasive to then start with the maximal trials of 30 seconds, 90 seconds, whatever. But if you just test the maximal sprint power and you estimate the maximal aerobic power with some of the approaches we have been discussing, then you can actually already model everything that's in between without actually having to do all these max trials. And secondly, if you do it like that, you have a standard testing approach where you do those two assessments, and then you can also identify with that same standard testing approach how things have shifted. So for example, has the APR decreased, or you have observed that it's decreased, but is that then due to a decrease in sprint power, or is it due to an increase in MAP, or both? So that's then things that you can start to evaluate with an actual standard testing protocol. So that's where I would see it a little bit different between the record power outputs and APR, where both are still, the record power outputs are very useful information, but it becomes more and more representative after you've collected a large amount of data. So if you want to know more acute changes, then using a testing protocol and determining the APR that way would give you a more realistic picture. So lastly, I've also been talking to some other colleagues, and there's also some colleagues that then observed that there's a bit of a mismatch between the record power outputs and the APR model power. And I've also seen that. So as I said a little bit before, I think the APR concept is a model with a single equation, single exponent equation, trying to model decrement in short duration power. That is quite a complex phenomenon. So that it's a model, it inevitably means that it won't fit everyone perfectly. If you look at a group level, it actually works fairly well, as we've been shown with the studies, but it might indeed be that on an individual level, there is some variation. So, but my approach has been, and what I would also advise, is that if you have a valid amount of data with record power profile data within the short duration domain from previous years, perhaps, then you could start to modify the exponent slightly within the formula to ensure it fits the pattern of that individual to a greater extent, and perhaps use that for future modeling approaches. And besides that, I think we just also have to realize that it will never be a perfect estimation of their max power for those durations, just because there's such a complex interaction of all those different factors, metabolic and mechanical and neuromuscular factors. So as long as we take that into account, that it's a model which is not perfect, and perhaps adjust a little bit where we need it, then it can still be useful in my view. So just to summarize a little bit how a testing battery could look like, that includes some of the elements that we have discussed. To start actually to build that house that I mentioned in one of the previous slides. So if you now start at the bottom, we firstly want to determine that upper limit of endurance capacity, which was then defined by the lactate threshold, if we remember back from that house model. This is one of the thresholds where you actually need some physiological data from. So this is one example, 6-minute steps, but they can also be longer at increasing power outputs, building up until critical power, for example, and then you take lactate measurements to determine the lactate threshold. And what we then typically look at is the initial increase of about 0.5 millimoles above baseline to determine that first shift in energy system contribution. And in my view, this is one of the variables that you actually have to assess using physiological data, because you can actually have two athletes that have the same critical power. So let's say they have a critical power of 400 watts, but then where their lactate threshold occurs can actually be substantially different depending on those individual characteristics. So we can't just estimate this lactate threshold based on a percentage of critical power, for example. That could be a starting point if you don't have this information, but in an ideal world, you would actually assess that. And then we move on to some of the maximal trials in the field. So this is just one example how you could spread out some of this across 3 sessions. Perhaps the first session could be to do a sprint profile, do the sprint profile testing that we discussed before. So there's a variety of sprints, different gearing ratios to determine sprint peak power output, which then sets the upper limit of the anaerobic reserve, and at the same time determine those power cadence and torque cadence profiles. What we then often do is also include a 1-minute test, just to get another measurement sort of within that short duration domain. And it can also be used to sort of spot check how well the anaerobic power reserve model actually predicts for this individual. Then in the last 2 test sessions, we actually do a number of maximal evenly paced trials of 3 minutes, 6 minutes, and 12 minutes. That could be 3 examples of durations that you could use. Now actually these 3 trials can then be used to determine the critical power. Which we have discussed also in the previous chapter. So a marker to set the boundary between sustainable and non-sustainable intensities. And there's a variety of models also for the critical power that you can use that we don't have to go through in too much detail, but those 3 trials could then be used to determine the critical power and W prime. And then we can use that 6-minute test as a maximal aerobic power estimate, again based on some of the stuff we just discussed. So if we then all assess that, we can then actually start to build our house, if you like. So we have the lactate threshold. Using that protocol that we discussed, we can determine the critical power using those field-based trials, the max trials 3, 6, and 12 minutes, for examples, or somewhere close to that duration. We have the maximum aerobic power, which can be set using that 6-minute power. You have the sprint peak power output determined by the sprint protocol that we discussed, and you can determine the anaerobic power reserve range. So then we have thresholds across a whole intensity continuum. And if you then want to do intervals at those different intensities and across the intensity across this spectrum, we can reference that to the closest threshold. So if we want to do intervals to improve lactate threshold, we can do that based on a percentage of the lactate threshold. And then we truly individualize the training intensity. Same if we want to do efforts to target the critical power, we can do efforts as a percentage or close to the critical power that we determined. Same goes for maximum aerobic power, and using then the anaerobic power reserve to set our intensities for these supra-maximal high-intensity interval training sessions. So this then gives you a very nice profile, which can be used for training prescription and training profiling. How we then interpret that and how this can subsequently be used in practice, that's what we then will cover in the last chapter. So to conclude, what we have now discussed is that actually every test, which I hopefully have made clear, should have a very clear goal and outcome, and every test that we should do should have the ability to have a direct impact on practice. There should be a consistency in your testing approach, and especially if you have a high consistency, you can actually grow a database over time, which then includes your normative values and reference values. Now the APR range can be determined using field-based trials, which I showed with the examples, maximal sprint trials, ideally at then those varying cadences to determine the sprint profile as well. And we have those different field-based protocols that exist to estimate maximum aerobic power. And which we also discussed quite extensively with this house model is that the APR testing should then complement sort of a larger testing battery, which also includes tests aiming to determine capabilities within longer duration domains. So for example, the critical power or the lactate threshold. So it can be a nice complementary tool within overall testing battery. So here you can again see the reference that were used for the content of this presentation. Again, referencing some of our own studies, and also the study that we discussed around the sprint profile testing. So then we've come to the end of this second chapter. Again, I want to thank you all for joining in, and I'm looking forward to see you all at the last chapter.